Swayam Prabha. Digital India. Educated India.
Dear all, last few classes I taught many problems how to solve, like many tutorials. So again I wanted to teach you some new technology like self-powered biosensors is really one more topic I will add in this course. So let's learn this. After that again I will start some few more tutorials that will help you for your exam preparations. And as I told, all the tutorials I just taught you, this is not just the solutions of your questions and answers. This is also kind of new concept you are getting. So today I will cover mainly the self-powered biosensors. So why we need the self-powered? So let's first discuss this issue. See, from the name itself you can understand, right? Your biosensors, it is self-powered and it don't need any extra power from outside. Generally battery operated your one sensor means it needs some energy, no, to get, but to suppose we are applying some potential 0.3 volt I am saying, or you are running a cyclic voltmeter, you need some energy. That energy you are getting from battery. When it's your potentiostat, your electronic circuit, everything, they need some energy that is battery operated. But this thing, somehow you visited a very rural area and that area is very far from like your advanced all the facility. You don't have much power also, or maybe some situations it may face, you don't have for few days the power. Then what happens? Then your sensor surface will not work. Now, for that purpose, you can develop a self-powered biosensor. Means you may have power backup, you may have battery, but still this can help you to generate some energy, and that energy can provide to the sensor and it can use without any battery. Let's come this. Our real sample we are using for diagnosis, no? Suppose blood sample. So it contains glucose, right? This glucose also has some energy. We can convert it with the help of like glucose oxidase, right? We can oxidize the glucose and that we are getting the electron. So here oxidations happen, right? Maybe you can choose another electrode where you can try the reductions. So one is the anode and another is the cathode. So if you have the anode and cathode, means your battery, means one battery you have. So you can use your real sample, and one component of your real sample like the glucose can help you to generate the energy. That is the topic for today's lecture. So anyhow, you can, but you have to generate one electrode where oxidations happen or another electrode where reductions happen. That I am going to show you. So it can basically help you a self-powered sensors, and also it can help you like continuous monitoring. Just see, in this case here one kind of design, your smartphone integrated systems. Suppose you have like a banded kind of very simple a biosensor chip. Suppose it can detect the glucose also, but it can detect the glucose at the same time it can generate the potential difference between the two electrodes like anode and cathode. You can develop, and based on, I mean, this is a kind of a small battery, like then you can integrate many this kind of cathode anode many step by many, then you may get the sufficient power. sufficient potential difference between the cathode and anode, and you can now get the enough power or enough energy to run your potentiostat or run your electronic device, that actually helping you to measure your biosensor target. Suppose in this case, here targeted the glucose, here it target glucose. So, you are going to detect the glucose. So, in this case, you can see in this simple sensor chip, where it will get the glucose? Maybe it can get from the interstitial fluid. I mean, it may have some small micro needle, and through this micro needle it will get the interstitial fluid and it contains glucose. From there it, or maybe from the other real sample you can think. I mean, this is just for a concept I am saying. So, any solution that contains the glucose you can try for potential difference and for cell power biosensor development. See here the design. This is a PCB based cell power device, PCB. So, here you can see the cathode and anode. So, anode here actually what we did, see, first we use some linker. Based on this linker we immobilize the glucose oxidase. They are the glucose oxidase enzyme. So, in the anode you can immobilize your glucose oxidase, and cathode you can use some like platinum or something. You can, I mean, there you may get oxygen reduction. So, one surface glucose oxidation, another surface oxygen reductions. You can see in this diagram, like here we can obtain a cell power biofuel cell, and when we use like 100 millimolar glucose, and we may get this power versus voltage, like how much power we can generate. This is a kind of a battery, right, that we can use for cell power biosensor development. That's it. One thing here I wanted to show you a very simplified circuit design. You can see here, actually see here a biofuel cell, that just last slide I taught you, like this biofuel, this is biofuel cell. So, this biofuel cell actually help generate the energy from glucose, and here you can again develop a like working electrodifferential current counterload. You can see your sensor. So, your actual biosensor here and actually your biofuel cell here. So, this is a very complete circuit where one part you can use your biofuel cell, another part you can use your biosensor. So, biosensor now means it will get the enough energy from the biofuel cell, it will harvest the energy, that energy actually we will use for the sensing applications. This technology we will use, and then finally we will try this wirelessly we can transfer the data. For that also you need energy, that's amplifications also we can do here in the circuit design. Who are actually from the electronic background, I will recommend them to think about this kind of the circuit design. So, this is because this is very much specialized for them. So, that is why I don't want to go very deep inside the circuit design, because mainly I just want to tell you the very generic concept. If you want a cell powered device, that is possible. So, one you can develop biofuel cell. So, one is the cathode development and the anode development based on the oxidation and reductions, and another part that is for biosensor. Okay, that is the design here in this slide. So, as I told you that we have to design a biosensor for cell power. See how we will start step by step. Here I will take some time to teach you how to design and how to develop a cell power device. So, first what you will do, you have to use, see here, some micro needle. So, micro needle based biosensor I taught you already. So they can help to collect the sample. So from their microneedle, from this microneedle surface, here you may get all the like your real sample, it will go to your sensor surface. But at the same time, this microneedle will help to get the your real sample that contain the glucose, and it may come in this case. So here you have the glucose oxidase in anode, and here you have the like some other enzyme like reductase kind of things, where oxygen will reduce. So there will be some potential difference. This is just I am summarizing this biofuel part, and you will differentiate the potential energy, and here is this total circuit diagram. So you may need some like analog processing amplifier. So that's things we need for the, because it is very small amount of potential you are developing. So you have to amplify basically, and you have to store this all the energy, and that energy you have to help, that energy will help you to run the full your biosensor. So one part is your like the microneedle development that will help to collect the sample. Then your second part will be your biofuel cell development, right? Biofuel cell development. Third step after biofuel cell development, you have to integrate the many cells, and you have to amplify, you have to store the energy, right? So you may need this. Also you may need the Bluetooth control, like communications. You can communicate the data via Bluetooth. So these all the electronic things you can design. So electronic part that you have to take care of. Then last thing is the biosensor. Okay. Biosensor means where you can sense your analyte. One very important, I mean in this case, is the PCB you can choose. It is very important and good substrate for designing the whole thing. What you will do, suppose you have the PCB, so here you have the working reference counter electrode, right? So this is your sensor surface. In the back side of this PCB, you can design this electronic whole part, where it can generate the energy, and front side you may have this sensor, and then on the top of this sensor you can use this passive pump or microfluidic and all the hydrogel based needles, everything you can use the top of the sensor. So top of the sensor, so this is, so one part will be your like micro needle, your microfluidics, everything in the top of the your PCB. Then in the in between middle you will have the biosensor, like for the glucose testing or maybe for any other target marker that you want to detect from the real sample. And back side of your PCB you may design the whole electronic part. Then your sensor will be ready for detection. So this biosensor you may try. Okay. See, this is as I told you, the cell power sensors, it is very smart technology. It is also IoT based, and here it is very much interdisciplinary. This part is very interdisciplinary. So I taught you until now like very basic biosensor. Maybe some of you like who knows the biology basic or very chemistry background, they can easily understand, they can easily fabricate. But now you have to collaborate for the full device development. Yes, these questions may come for this advanced biosensor or full device development things, because our whole translational research, you can remember this kind of research is the translational research, right? Translational. So we can easily translate also from easily bench to bedside applications. See, and there is a main two pillar I taught, one is the collaborations. One of the main pillar is the collaboration. So maybe you are expert for the sensor development, right? You can easily develop the defined nanomaterial. Then you can easily conjugate the antibody but you don't know maybe the circuit design. So what you will do, just develop the sensor. You have to collaborate with some basic electronics, or you are expert in the electronics, because for this IoT enabled, for through the transfer the data through the Bluetooth, you need some this kind of design. That definitely you have to first optimizations required. How many biofuel cell you have to use to get the accurate potential difference, that also you have to think. There are so many factors. Okay. And in the biofuel cell, where maybe if you are the basic biologist or chemist, here maybe you can take part, right? Like which material you can use for the cathode, which material you can use for the anode. See, sometimes maybe you may not get the potential difference, that you can take part. Also, let's try to avoid the using the enzyme like glucose oxidase or other bilirubin or other oxidase kind of thing, or reductase. They are enzyme, they may denature easily, right? So it is preferable if you can try some non-enzymatic. Generally we prefer here some chemical. Many chemicals is available, so you can try here in the oxidations where you need the oxidation and where you need the reduction. Then easily you can make the potential difference between cathode and anode. So something like this, like hydroquinone easily convert to the benzoquinone. So quinone based compound. So here is also electron transfer, right? So this kind of reactions also can help to generate the potential difference. So next class maybe I can show you the more reagent. So in this class I cannot show everything. Let's try to understand the first principle today, and then next class I will show you the many other reagent, that is enzymeless, enzymeless or non-enzymatic. So one basic things, you can try some very simple chemicals that can help you to generate the potential difference. Also at the same time you may think like here is your potential, like your all the battery, right? Small battery, and maybe near you can try here biosensor. So your battery and biosensor are very near, and they can help each other for the development. And these things just is really important in the current situations, like it is called continuous monitoring, right? Why we need the continuous monitoring? Because sometimes, especially for the glucose concentration depends on your exercise, depends on your food habit, right? In the morning one different, after taking some food it will be different, and really means you need some insulin or not. Where the diabetic, they may need the insulin, right, just before the meal. So you may have the continuous data for the whole day, and then you can decide your food habit, you can decide. So that's why this kind of device is really important, this self power biosensor. This is the advanced technology, so you can apply. Okay, and this slide just I taught you a very basic scheme, but this is kind of the plan you can try. That is my goal actually today in this lecture, that how to design a self power biosensor. And say, because in this class maybe some of you are the very in the UG background, maybe PG background, who want to go for the higher study. You may think some kind of project like this, development of self power biosensor for, so last cases I tried the glucose detections, right? You may try this one. Suppose if you try in the urine sample, so you may think the creatine detection. Creatine, that is this, it causes the like problem for kidney, right? Creatine detection also you can try, creatinine. So that is also very important factor, so that you can think like I am just giving another project like this way. So same way, so what you will do, you can think about the creatine detections on a biosensor, and there is different enzyme available for the creatine or maybe some others, but I will recommend let's develop some nanoparticle for like creatinine. But thing is there, while although it is very easy to say like let's develop some non-enzymatic biosensor, like nanoparticle, they are the non-enzymatic biosensor, but development of a nanoparticle and getting the specific data is really crucial factor. What? The specificity, specific biosensor is really important. Suppose I developed a nanoparticle, NPS, suppose X nanoparticle I developed, right? So I fabricated on the sensor surface this X nanoparticle and I tried the creatinine, and I got the very good electron transfer rate, and I changed the concentrations. Once you change the concentration, suppose you are getting the chronoamperometry like this, you are getting the changes, right? Different creatinine, you are getting the current also changes, and you got the very good calibration curve also, like very good straight line also you got like creatinine detection. Here is the suppose current and here is the concentration of creatinine, right? But when you check the actual real sample, suppose you are using the urine sample, right? Or maybe you are using serum sample. See, the serum and urine, it may contain some other species. If those species also react with this nanomaterial, then your whole sensor actually become useless. So what happens? Suppose in your serum sample contain the glucose, your X nanoparticle also reacting with the glucose, and it is also showing the current change. So suppose in your real samples contain like 10 millimolar glucose, others contain maybe 12 millimolar glucose. So because of 2 millimolar glucose change, you may get the different current. So it will misguide it. It will misguide you. That's why the specificity means this nanoparticle should not react with other interfering species present in the real sample. That's why we always recommending, once your concept done, means suppose you developed a nanomaterial, some new nanomaterial, and your creatine reacting very good. You are fantastic that your first work is done, but you can't say that your means now you can make the device. Before making the device, you just make a real sample and check the data. And if you see that now actually real sample other component also reacting, then you have to go for the optimization. This is the very common problem for development non-enzymatic biosensor. It may react with your target. It may react, you may get very good data, you may get very good sequence, everything done. But if you see that your other component, the real sample is reacting, then let's optimize your whole sensor. Your whole sensor should be optimized in real sample. How? So just check real sample which component present. Those component is really reacting on this sensor surface or not. Then which potential you are applying actually? Maybe see because you are applying some potential, no? I am showing this one. Suppose this is your sensor surface. You have some specific, you are thinking your nanomaterial is very specific. So here you are applying 0.3 volt for the chronoamperometry case. But in that potential, if it is showing the glucose oxidations in your real sample content, let's apply like different potential. Let's go to the near zero, as I told you, no? Like 0.1 volt you can try, 0 volt you can try, minus 0.1 volt you can try. Then let's find out which potential is the best for the real sample. Then use that potential for the creatine detections. And still after this potential, say once you decrease the potential, then your background definitely will decrease, but signal also will decrease. That also a problem. Because if your signal also decrease, then your signal to background means you are getting actually your sensitivity. So if you lose the sensitivity, then also it can cause a problem for your sensor development. What you can do, you just think about now the design of the nanoparticle now. So you can design nanoparticles with some different metal base. Different metal, here maybe you have tried like gold. Now here you can try with gold with some other decoration, or maybe some other alloy type, or maybe change the gold with something else. Try and then check again the same way that creatine is reacting or not. Then again the same way use the real sample. Let's get that all the interference data that we are getting with the other nanoparticle, here also you are getting the similar way or not. See, many, I think you may ask these very common questions. Sir, we can go for this biosensor development, these things, but as you are asking the real sample, so that we can go for the final optimization. But handling real samples, there is a one issue, the ethical clearance. Ethical clearance that you have to very much cautious, because you are developing biosensor, right? So one day maybe I will show you again what is the ethical clearance. The ethical clearance you should have. Ethical clearance, suppose you are using blood samples. You are collecting from maybe from 10 patients. Some patients, they may have some infectious disease, right? So in a laboratory they may be affected, right? So you should have, you should follow the proper protocol of the handling of this all the real samples. This is one factor. And how to dispose, maybe you handle properly the real sample, but you are not disposing properly. So there is one committee always there, that is ethical committee. They will help you, or they will give you proper guidance, or they will check you are following the proper guidance or not. Means the disposal of your sensor waste, means after use, you are wasting, you are throwing your all the component like is randomly. Otherwise, see, if you throw in just randomly, means someone also can be affected with some infectious disease. Maybe from it can come from other patient. You may use like some like some saliva sample. That saliva may contain some COVID or something. It may again spread to someone else, right? So we have to check properly that who will handle this real sample. He or she will be very much cautious about this, and he should or she should know how to handle this, and he should not dispose randomly. He should properly dispose it. That everything controlled by the ethical committee, and that's why we will take the approval from the ethical committee. That's whenever you already done. That's why when we have done our sensor development, and finally at the end of the time we are thinking, let's use the real sample, let's validate it. But it is not the good plan. You just think from the beginning of the real sample. So once you almost, suppose you already made a nanomaterial surface that is very specific, and you already get some data, let's now immediately try some real sample. Let's see their behavior on the sensor surface. Sometimes real sample is behaving fully different than whatever you are optimizing with your buffer sample. So that's why you should have some plan used at the very beginning. Otherwise, at the end of the development, again you may come back for your whole sensor development. You have to start again from the beginning. So you should have some information if you use the real data. So this is the conclusion for today's. That today I taught like self-power sensor, self-power biosensor. So this is really important, because where you don't have really the power supply, but in a very rural area, but maybe somewhere you went, you may not get the power for the longer time, there you can try. And this is also very much useful for continuous monitoring that I taught today. So continuous monitoring. And another things today I taught you, that is the how to use the real sample, and who can guide you. Maybe if you go any good institute, they have their own ethical committee, they will guide you. So you have to go through proper guidelines. WHO also, the World Health Organization, they have very good proper guideline. Once you already developed your biosensor, so which biosensor develop some target, suppose some COVID virus related some biosensor you develop, please go to the WHO protocol. Let's check how they what is their advice, and let's follow this and then go for the real sample handling. But that should come actually not at the end stage of your sensor development. You have to think this one in the middle, because you may need to change so many parameters. So that's it. Once you develop something, let's try to use this real sample. Okay, it's done. Then again complete the sensor development. Then finally validate the whole sensor with real sample. Okay, so that's the main concept. You please try to remember. And next class again I will show you some new technique, some new tutorial also, again some new problems I will give, and you will learn something new design and you can think independently. Okay, that's all. Thank you very much for today's topic. Thank you.